this is what we talked about last time, and we'll just do one, maybe two examples of a homogeneous linear equation with constant coefficients. And here's one example where there's initial values. So let's try this one and see how well we do. Remember that the process that we went through last time is a process that you don't necessarily need to go through every single time. And we just have to try to remember the summary. I don't know if you remember the summary off the top of your head, but it should be written in your notes or whatever. It's available here. But you know, it boils down to if you have two real roots, then your answer is exponential. If you have a real root, one real root that's repeated, then it's the exponential with x times the exponential. And the third case is that if you have complex conjugates, then you have sines and cosines. Okay? And that extends beyond the second order differential equations. If you have higher orders, fourth order, then that's going to be the same case. So we'll do one of those higher order ones. And the key is just to be able to factor the polynomial. All right, so here is our example. We have y double prime plus y is equal to 0. And we could think about going through the process, but we can immediately jump to the characteristic equation. And the characteristic equation says that the order and the power matches, right? So this is m to the second power plus m to the 0 power. And the constant is just 1 there, is equal to 0. So if you try solving for m using whatever it is you need to use, you're going to get positive and negative I, right? So those are just imaginary numbers. Complex conjugates. So we're in the third case. We're using sines and cosines. The coefficient of I is 1, so it'll just be sine x and cosine x. Huh. We're done. Well, almost. But that's your general solution. So you're looking for the solution based on this. You can make a note that these are complex conjugates. And so your fundamental solution is going to be a set that has the sine and the cosine of 1 times x. I guess we're using theta for your independent variable here, so I'll use theta as well. So there's no real part, so e to the 0 is 1. That would have been multiplied in front of the sines and cosines. And then the imaginary part, again, the coefficient is 1, so that's 1 times theta. So that's a fundamental solution. Your general solution will look like this. Y is equal to some arbitrary constant times one of the fundamental solutions plus another arbitrary constant times your other fundamental solution. And then this will give you with the initial conditions, it'll help you solve for C1 and C2. This is a second order differential equation, so not only do we have two fundamental solutions, but we should expect two arbitrary constants. That's a C1 and C2. And so you would need two equations to solve for those two unknown arbitrary constants. Okay, so now we're going to use your initial condition. IC is when theta is equal to pi over 3, your y is equal to 0, and when theta, this is a point, and then here is a derivative, so we need the derivative of this thing. Kind of got ahead of myself there. So pi over 3, and then the y prime is equal to 2. All right, so we need the derivative of y. Our general solution, the C1 constant stays there. Derivative of cosine is negative sine. And derivative of sine is positive cosine. And then we need to put pi over 3 into both of these equations. So if we put pi over 3 into the first equation, cosine, sine, oh no, cosine. I'm looking at y itself. Cosine of pi over 3, is it 1/2 or root 3 over 2? It's not 45. What is it? 1/2? So we got, for this one, we put into the y equation, we should get 0. So this is 1/2 C1 plus, I'm assuming this is root 3 over 2, C2 is equal to 0. That's from the first equation. From the derivative equation, we have negative sine first, and so that's sine of pi over 3 is root 3 over 2 with a negative root 3 over 2, C1, and then the cosine of cosine of pi over 3 is 1/2 C2 is equal to 0. So you got two equations and two, oh, not 0. What is it? Should equal to 2. So you have two equations and two unknowns, and solve for it the best you can using, I don't know, whatever. You can use linear algebra, you can use just simple substitution, solve for C1 and C2. Anybody do it yet? Can you just tell me the answer? I have to do it. I'll do a substitution. I'll solve for C1 for the first one. C1 is equal to negative root 3 over 2. C2 divided by 1/2. So that's multiplied by 2 over 1. The 2's cancel. So C1 is equal to negative root 3 C2. I'll put that into the second equation. Negative root 3 over 2 C1. Oops, I want to replace C1 with negative root 3 C2 plus 1/2 C2 is equal to 2. Let's continue solving for that. That's positive 3 over 2, 3/2 C2 plus 1/2 C2 is equal to 2. So 2 C2 divided by 2 is just C2 is equal to 1. And now C2 is equal to 1, so C1 is equal to root 3 over, the 2's canceled already. So negative root 3 times C2 negative root 3 times 1, negative root 3. Right? So your complete solution to the IVP, the initial value problem, is simply you putting in C1 and C2. So C1 is negative root 3 cosine theta, and then C2 is positive 1 sine theta, and that's it. Okay? All right. Any questions? So this work right now that's on the screen is really just the initial value problem. It's solving for C1 and C2. I guess the important calculus part is over here, finding the roots of the equation and then just coming up with the solutions, the fundamental solution. This is FUND, by the way, fund, period, fundamental. Okay? All right, let's move on. Let's do one of these higher order ones. Let's see, 21 through 28. Don't pick. 24, 25? $24? So this is a fourth order differential equation, no initial condition, so we just have, or whatever our answer is will be left in general form. We have the fourth derivative of y minus 2y double prime plus y is equal to 0. Homogeneous, constant coefficients, linear. All right, we're good to go. Characteristic equation, m to the fourth minus 2m squared plus 1 is equal to 0. Oh, man. Squared plus 1 squared. What? Is it m minus 1 to the fourth? Wait, do you guys agree with Nick, or should we? Was that right? So it'll be m squared minus 1. Are we good with this? Did you do it on your calculator? M squared plus 1, m squared minus 1. Yeah. That was right? Yeah, so it was right. So it'll be m squared minus 1 quantity squared, and then you factor m minus 1 at plus 1. So Nick was right. I mean, the calculator was right. Hey, that's not fair if you get to use that calculator, huh? So maybe I'll factor it on the test for you. Yeah. So I don't care how you factor, I just wanted you to be able to factor. All right, we have 2 repeated roots, it looks like. So m is equal to 1 and m is equal to negative 1 are repeated roots. And we should note that this is repeating twice, because if there's a repeated root that repeats 3 times, then you kind of just keep adding on or adding another factor to the process. So we should expect 4 solutions. According to this, m is equal to 1. One of our solutions is going to be e to the 1 times x. I guess we'll use x. And according to this m is equal to negative 1, another solution is e to the negative x. Okay, so because maybe I should have done it first going down. Yeah, same thing. Well, that would be for this one. The fact that it's repeating means I need to get another solution out of that. So that my third one is x e to the x. Remember, if you have a repeated root, you just tack on another x for the number of repetitions. If it's repeated 3 times, like it would have been m minus 1 to the 3rd power. If it's repeated 3 times, then your fundamental solutions will have e to the x e to the x, and then x squared e to the x, yeah. This one, it only repeats twice, but I explicitly wrote twice there because it tells me how many times I need to write this down. And then the last one, we need 4, right? This is a 4th order differential equation. Our last one is just, because this also repeats, it'll be x e to the negative x. Okay? So we're basically done. We just need to write it out neatly. Your general solution for your differential equation, this is a G, is just a linear combination of this. So 4th order, so we'll have 4 unknown coefficients. We'll call it C1, e to the x, plus C2, e to the negative x, plus C3, x e to the x, plus C4, x e to the negative x. And the order doesn't matter. We're adding. Addition is commutative, so it doesn't matter which is which and where goes where. That's it. Okay? Easy, huh? All right. So we laid down our groundwork. We talked about superposition principles and stuff like that. And then now we're dealing with homogeneous differential equations. Still dealing with constant coefficients, linear constant coefficients. And so now we're going to extend it to take a look at when we have a non-homogeneous. So the right-hand side is no longer equal to 0. So in doing that, it's going to be a little bit trickier, a little bit more difficult. But we're going to need this information where we take a look at the homogeneous counterpart of your differential equation. Okay? Not only that, for this beginning part, we're going to be restricted to a handful of possible right-hand sides. So the right-hand side has to be a nice special function. And for starters, we're going to assume that the right-hand side is a polynomial, an exponential, or a sine or a cosine trig function. So at this point, we're not ready to dive into when the right-hand side is a log function or the right-hand side is a 1 over x, a rational function, or anything like that. We're going to start off with something simple. And in doing so, we will find a particular solution to non-homogeneous differential equations where your right-hand side of the differential equation is either a polynomial an exponential function. It could be any, raised to the alpha times x, whatever alpha is. Alpha can be anything. Or a sine and a cosine function. Now these things can have coefficients here too. Sine of 2x, sine of negative 3x, or whatever. So we're not going to tackle the other types of functions yet, like 1 over x, ln x. And we can't even do the combinations of sines and cosines and the ratios, so the tangents and secants and stuff like that. So we're not going to deal with that just yet. We will eventually. It's going to get harder. And we'll take a look at how to approach some of these other functions. But for right now, we'll deal with the simpler functions. So remember, if you have a set of fundamental solutions, and remember that the fundamental solutions come from the homogeneous So the first part in doing this is finding the fundamental solutions, and then after that we're going to find a particular solution. And that particular solution will work, should work, better work for the non-homogeneous differential equation. And then after we do that, our general solution becomes a linear combination of the fundamental solutions and added on that one general or one particular solution that we found. So our focus here is to find a particular solution, y sub p. We're going to find one particular solution. After we find that, then our last step is to write our answer with the fundamental solutions. Okay? So what we're going to do is we're going to assume that your particular solution is some linear combination or some constant times g of x, whatever g of x is equal to. All right, it's a little trickier than that, though. If g of x is a polynomial, then we have to write the general polynomial. So if the polynomial was x squared, for example, then we have to write ax squared. So example, if your polynomial g of x is equal to x squared, then your guess for the yp is equal to ax squared plus bx plus c. So when we talk about a quadratic equation, a quadratic polynomial, second degree polynomial, we have to allow for the linear and the constant terms as well. Okay? If it's an exponential function, then it's just an exponential function. But we'll throw that constant in front of that. And if it's one of the trig, then we have to, if it's either one of them, then our general guess is going to be a linear combination of both of them, regardless. So yp will be ax, or a sine x, plus b cosine x. Okay? So we're going to assume that our solutions are going to match the right-hand side somehow, except maybe with some constants and some added terms. And then what we're going to do is we're going to run our guess, regardless of what our guess might be, to run our guess into that differential equation and then solve for those constants, a, b, c, or a little combination of whatever. Is that making sense? All right. Well, let's try a problem. It makes a lot more sense when we start doing these things. This is one of those things where the theory is theoretical. Oh, well, look, we have a whole bunch of them. Let's start with number 4, for example. By the way, this whole idea of linearly independent also plays a part into this. So I didn't mention that if it's your fundamental solution is dependent with your g of x, then you have to do something different too. We'll see if we get into any of those. All right, let's first imagine this as a homogeneous differential equation and find our general solution for a homogeneous differential, at least the fundamental solutions. So let's imagine y double prime plus y prime minus 6y is equal to 0 and find solutions to that to start with. So our characteristic equation is m squared plus m minus 6. And then we factor or whatever 3 and 2, right? So let's go m plus 3, m minus 2. So we got a couple of solutions, positive 2 and negative 3. If that's wrong, say it now, because I'm moving on. Good? All right. So our fundamental solution is going to be a set of functions, e to the 2x and e to the negative 2x. Oh, negative 3x. Okay? So in the end, I'll have my fundamental solution as part of my solution to this differential equation. So that part is done. Now we need to find yp, one particular solution that will satisfy this differential equation. And for this, we're going to need to assume, since this is our g of x, it's 2x, assume yp is equal to what? What? Ax? Not quite. Ax plus b. So if it's a linear term, which in this case it is, 2x is a linear term, then we want your solution, your particular solution, to have the form of a general linear term. So that's included this constant at the end. All right? So our task now is to solve for a and b. We're going to take two derivatives to plug it back into the differential equation. So yp prime is a, right? And then yp double prime is 0. So that's nice. We got 0 plus a and then y is ax plus b is equal to 2x. So from our differential equation, we replace the second derivative, the first derivative in the original function with our particular solution guess. And then we're going to attempt to solve for a and b. Does it look familiar? Remember this? A minus 6ax minus 6b is equal to 2x. And if you just arrange it so that the coefficients match up, negative 6a times x plus a minus 6b is equal to 2x plus 0. So looking at the coefficients of x squareds, or I guess I just have x. Look at the coefficients of x and look at the constant terms. We're going to set up a couple of equations with a couple of unknowns and then solve for the unknowns. I have minus 6a is equal to 2. That's easy. And I also have a minus 6b is equal to 0. So a is equal to negative 1/3. And if a is equal to negative 1/3, then b is equal to I got positive 1/2. Is that right? No. 1/18th? I was going to say 1/6. 1/18th? Negative or positive? Negative. Negative 1/18th? Second? Anybody? Going once? Twice? Yes. Ah, good. All right. We did it. We found a particular solution. Our particular solution, YP, I'll say particular solution is negative 1/3 times x minus 1/18. Okay? So if this problem was just asking for the particular solution, that's my answer. I'm done. But that's not the general solution to the differential equation. The general solution, according to the superposition principle, says that I have to get my linear combination of my fundamental solutions and then tack on my YP, particular solution. So that's an easy last step, as long as I can see the fundamental solution. So general solution to the non-homogeneous differential equation is equal to, I'm going to have this is a second order differential equation, so I should expect two arbitrary constants, a C1 e to the 2x plus C2 e to the negative 3x plus, and then the y that we just found. I guess that would be a negative minus 1/3 x minus 1/18. And I would check this if I had more time. But if you were to take this, take the derivative a couple times, plug it back into the very original non-homogeneous differential equation that we got, we should get this thing to work out. Okay? That was fun. You think? Yeah. Could be playing video games. Could be watching TV. Could be drinking. Well, you could drink and still do your homework up to a certain point. Not that I'm being recorded here. Not that I'm condoning drinking and deriving. All right, let's take a look at another problem. They jump on those e to the x's already. Let's do one with a trig function. Four y double prime minus 4y prime minus 3y is equal to cosine 2x. So first, take care of your homogeneous counterparts. Let's begin by looking at 4y double prime minus 4y prime minus 3y equal to 0. Just looking at the homogeneous portion of this. Characteristic equation, 4m squared minus 4m minus 3. And I think I might need to use a quadratic formula for this. Negative b plus and minus the square root of b squared minus 4 A is 4. B is negative 3, so that's going to make our inside positive. So I thought I was going to come up with a sine or a cosine here. Complex conjugates, but it looks like it's going to be positive. Divided by 2a. All right, so this is 4 plus and minus something in here. 16. What? Under the square root? Nice. So that's 8, right? Ah, I could have factored this. Huh. So my two solutions. Three halves and 1/2. Three halves and negative 1/2. Will you get confirmation on that? Yeah? All right. Okay, so we can build our fundamental solution set. Right, negative, negative. So is this cool? All right. All right, so those are your m. They're coefficients for your exponential functions, not the front coefficients, but the power of the exponential function. So we have e to the 3/2 x and e to the negative 1/2 x. Okay. I don't know if I'm telling you this explicitly, but as I'm finding the fundamental solutions, I'm also comparing it to make sure it's not linearly dependent with your g of x function. Because if I, for some reason, got a sine and cosine 2x and sine 2x for the fundamental solution here, I'm going to have a little bit of a problem matching this up because that's linearly dependent with these two fundamental solutions, had I gotten a sine and a cosine. Had I gotten a sine 2x and a cosine 2x. That makes your problem a little bit more difficult. And so it is important to look at your fundamental solution and your g of x before you proceed, because that's going to make a difference. All right. Let us now try to find our particular solution. Our guess for our particular solution should be what? A times cosine 2x. Yes. Plus b. Don't forget the sine and the cosine. When you take derivatives of sines and cosines, they're each other's derivatives. So you have to account for the possibility of the sines and cosines popping up. Okay? Now you're going to need to solve for a and b here. So let's see. Let's take derivatives, because we need to put it back into the original equation. So derivative of cosine is negative sine. So negative 2a sine 2x plus 2b cosine 2x. Second derivative, negative 4a cosine 2x minus 4b sine 2x. Painfully put it into put it into the differential equation and then tediously work it out. Too many adverbs around. 4 times this big mess minus 4 times the second big mess minus 3 times the original big mess this should equal to cosine 2x. You can imagine there's a sine 2x there that's being multiplied by 0, right? Because that's kind of like what's happening. So it looks like I'm interested in grouping the sines and the cosines separately. So let me just write down on one side of the equation, on the right-hand side, I have 1 times cosine 2x plus 0 times sine 2x. That's my right hand of the equation. And so on the left-hand side, somehow, I need to simplify this to be some linear combination of sine 2x and cosine 2x. And they would have coefficients in front that would have a's and b's that I'll need to set equal to 0 and 1. What are they? Let's gather all the cosines together. I have a 16a positive. The cosine here is a negative 8b. For which one? Oh, I lost the negative sign. Thank you. Negative 16a, negative 8b, and then the cosine here is a negative 3a, negative 19a put together. I don't know. I don't know anymore. This one? Okay, so is this cool? Negative 8, so negative 4 and positive 2, negative 8. And then I have negative 3, and then just the a, so that's just negative 3a. And now I'm about to combine the negative 16a minus 3a, 19, negative 19, minus 8b. So that's the coefficient of the cosine that I have for the left side, and that should equal a 1 according to the coefficient on the right side. All right, let's find the coefficients of the sine. It's negative 16b for the sine. The sine, negative, negative, positive 8a. And then the sine, negative 3b. So the b's get together for 19, negative, and then this is 8a minus 19b. Does that look okay? Okay. We have two equations and two unknowns. Negative 19a minus 8b equals 1. That's the coefficient of a cosine. We have 8a minus 19b is equal to 0, coefficient of the sine. I think this might be too complicated to try to do the addition method. So maybe I'll just solve for b or a on the second one. Say a is equal to positive 19b over 8, and then put that back into the first one. Negative 19a minus 8b is equal to 1, and try to solve for b here. Oh, what's 19 squared? $361? 361b negative over 8. So I need common denominators, 64b over 8. 425. So negative 425 over 8, negative 8 over 425. Maybe you guys should tutor algebra and have your algebra students work this out for you. That's what I do. I teach and then I have my students work it out for me. Is this correct? All right, so that's that's B, and A is equal to 19 over 8 times this big fraction, negative 8 over 425. Looks like this will end up being negative, and the 8's cancel, negative 19 over 425. Got to box these answers because you lose them along the way, right? Sure. All right, we got our A, we got our B, we got our fundamental solutions. We are done, except for writing the answer. General solution. I didn't bother writing down the YP. YP is this number times cosine, this number times sine. So I'm going to write it all together. Our general solution involves our fundamental solutions, C1 e to the 3/2 x plus C2 e to the negative 1/2 x. So those are your fundamental solutions, the linear combination of your fundamental solutions. Your particular solution is A, just to make sure we did the cosine first, right? So A minus 19 over 425 times cosine 2x plus B, that's a negative 8 over 425 times the sine of 2x. There you go. How long is this on your paper? It's not even a page yet, huh? Wait till we do series. You're doing 2 pages worth of one problem. Fun. Not only that, it's series. The best part of Calc 2, right? Oh boy. All right, we good? Isn't this fun? Yay. All right. Now, it gets a little bit more complicated when, we're focusing on polynomials, just exponential functions, just sine or cosine. Conceivably, you could have a product of sines and cosines and stuff like that. Let's see if I could pick something easy first. Yeah. Number 6 or 7 is about the same amount of work, I think. Just depends on your what you end up doing. Maybe we should do one of your homework problems. Sure. We'll go for that, huh? We are in section 4.4. 4.4. Oh, there's a quiz there, huh? That's not the quiz we're going to take. Okay. Done. All right, let's take a look at number 2. Number 2 is a combination of a polynomial, and not just adding. If it was adding combination, you kind of treat them separately and solve for them. But here, it's a product of x squared times e to the 5x. So we have a little bit of an issue there. So we have to be kind of tricky in determining our particular solution, our guess for your particular solution. The easy part, whenever you're stuck, you just start with the fundamental solution. You know you get some points in that for the test. So let's start with the fundamental solution. And for that, we focus on y double prime plus 5y is equal to 0. Characteristic equation. Bring it over to the other side, you'll get a -5. Take the square root, you'll get imaginary numbers. So your m is equal to plus and minus square root of 5i. Or, when in doubt, just use a quadratic formula and then work things out to make sure that you're not going to miss anything. But I think this is, I think these are our solutions for our characteristic equation. So we just need to plug that in. Imaginary numbers, complex conjugates, there's no real part, so it's just going to be a plain sine and cosine. If there was a real part here, like a 1 plus or minus square root of 5i, then we have e to the x times sine, e to the x times cosine. Okay, but there is no real part, 0, e to the 0 is 1, so it just gets ignored. Your fundamental solution set. Looks like cosine root 5x and sine root 5x. And as I look at the right-hand side of your non-homogeneous differential equation, I don't see any sines and cosines, so there's not that issue yet, that issue that I've been kind of alluding to, but we haven't seen an example of that yet. But I always want to check for that. Okay, now I have x squared e to the 5x. What is going to be my guess for the particular solution? It's tricky now because there's a x squared. So I definitely want an e to the 5x there in this picture. But I have a polynomial, not only a polynomial, but more specifically a second degree polynomial. So remember how we want to express a second degree polynomial, right? ax squared plus bx plus c. So ax squared plus bx plus c is going to get multiplied with this. Now I really want to use Mathematica because I have to take two derivatives, and that's going to involve a product rule and blah, blah, blah. But I have to show you this is doable by hand, right? So let's do it by hand. Okay. I don't have a first derivative, but I do have a second derivative, so I still need to take the derivative to get to the second derivative. So first derivative, derivative of the first, that's 2ax plus b times the second, e to the 5x. Plus the first, the whole thing, ax squared plus bx plus c times the derivative of the second, so that's e to the 5x times 5. Now I need to do the second derivative, so let's take the derivative again. Good thing I have a long line here. All right, so I have two product rules. Oh, you know what? I can try to combine them. Instead of doing two product rules. Let me do one quick simplification, of factoring out of e to the 5x. I don't know if this is any easier. Ah, screw it. Let's go back. two product rule, here we go. Derivative of the first, that's 2a. X is still the variable. Remember, you got a's and b's floating around. They look like variables. Those are just coefficients, undetermined coefficients, as a matter of fact. All right, derivative of the first times the second, plus the first, times derivative of the second. Okay, that's 1. Next one, I have a 5 here too that I'm playing around with. So derivative of the first, I'll keep that 5 outside. 2ax plus b times the second, 5e to the 5x plus the first. Plus the derivative of the second. So you guys do your derivatives maybe a little bit differently than mine. As long as we're getting the same result, we're all good. All right, it looks like the e to the 5x is something that's common in all of them, so let's just take that out. See what we got left. We can also imagine that this general polynomial ax squared plus bx plus c can be expanded here, where a is equal to negative 180, b is equal to 0, c is equal to 0 for the right-hand side. And so I'm going to want to gather all my x squareds together, all my x's together, and all my constant terms together. Okay? So that's what I will be looking for. So, x squareds. I think I only have one x squared here, right? Nothing else is being x squared. So that's a 5, that's 25. A times x squared. We good? See that? X. Now let's start over here. Nothing here. There's an x there. Could you see it? Just in case you couldn't see that x, it should have been there. Yeah. All right. So counting all the x's, I have a 5 times 2, that's 10a with an x. I have another positive 10, no, this 5 times 5 is 25 times another 5 is that 50? 50ax for this, with a combination of all those. And then I have this b with a 5b. Did I cover all my x's? So 50 plus 10 is 60, 60a plus 5b. $25? Still 60a, right? 60a. Oh, there's a 5 here. 5, 25. Plus 25b. Does that look okay now? All right. All right, I need another color. Orange. Now the constant terms. I have a 2a. I have a 5 times 5b, 25b. I have a 5 times 5c, 25c. Does that look okay? Did I catch everything? All right, so this is a 2a plus 25b plus 25c C times that. What's on the other side? The other side is negative 180 x squared e to the 5x. The what? Yes, you do. All from alpha. All right, bummer. So this is your y prime, or y double prime. Now we need to add the 5y. So 5y. 5 times a x squared plus bx plus c e to the 5x. Oh. All right, so I got 25a and then another 5a, so that's 30a, right? Plus, now for my b's, I have 60a plus 25b, and then add another 5b for my x's. So what color was that? That was green. I have to go find green again. Green. So 60a plus 30b. Right? Oh, now I get my purple back. Oh, this is so confusing. Plus, now I add C, I add another 5C. So I got my 2A plus 25B plus 25C and another 5C, so that's 30C. And that's it. Oh, not that this matters, but this whole thing is being multiplied by e to the 5x. Right? Now this whole thing is supposed to be equal to the right-hand side. And what's the right-hand side? The right-hand side, let's see if I can match colors, is 180 x squared times e to the x, e to the 5x. Plus 0 times x times e to the 5x plus another 0 times e to the 5x. There we go. So your system is going to look like 3a 30a is equal to negative 180. Right, you can find your a value here already. What's a equal to? Negative 6 or 66? Negative 6. Let's box that. We know that for the x's, we got 60a plus 30b is equal to 0. And since we know what a is equal to, we can plug that in. 60 times negative 6 plus 30b is equal to 0, and this will help us find b already. 360 divided by 3 is 120, or just call it 12. And it's a positive 12, right? Let's box that. And then finally, we have 2a plus 25b plus 30c is also equal to 0. And we have values for a and b, so that's 2a, that's negative 6, plus 25 times 12, that was b, plus 30c is equal to 0, so c is equal to this big mess divided by 30. Anybody? (9.6). Negative 9. Is there a fraction for that? And it's negative, right? All right, there we go. We have our particular solution, and tacked along with our general solution, or your fundamental solution, we have our final answer. General solution. Are they looking for the general solution? Solve for it. So we want the general solution. So we want the cosine C1 times the cosine of root 5x plus C2 sine of root 5x plus, now I have a combination of minus 6x squared plus 12x minus 48 over 5 times e to the 5x. I don't want to type this in. Scary. What? Feel like we need to, huh? Oh well, class is over. That's not. C1. Cosine square root of 5 x plus C2 sine square root of 5 x plus negative 6 x squared plus 12, whoa, plus 12x minus 48 over 5, close that parentheses and multiply it with e to the 5x. It's right. It's got to be right. What? It's green. Oh.
Try 4x and negative 14 over 5.
4x where?
You know, right there. Try 4x and then negative 14 over 15.
Negative
14 over 15.
14 over 15. You mean I did some algebra wrong? Huh. Thanks, Elliot. Woohoo! All right. Where's the mistake?
I think it was in the
Obviously, right here. You mean the first step? It's here, right? The A is correct.
No, the A is right, but
20A, 25B.
So when you down there, we have 60A plus 25BX minus 20A.
Oh. Ah. You should assume that I'm doing things wrong.
Okay.
What was this again?
That was 20.
20. Back in derivatives. Well, thank you for being a little bit more meticulous than, a lot more meticulous than me.
And then it was 10 and over it was 10 being plus 2A plus 10 B plus 25C.
2A, this one, plus 10,
Yes.
and 25C is still a 25C. So, okay, a couple of errors here that really jack up your problem. You know, you got the mechanics all down, and you just have to be precise now with your tedious algebra work. So, here's a lesson for you. Be careful. Have a good weekend.